Welcome to the Shikasa Motor channel. This channel provides easy-to-understand explanations of car mechanisms. This video provides an overview of 4 key hybrid systems, takes a detailed look at series hybrids, and compares Nissan's second and third generation epower with their main competitors. Hybrid systems can be classified into 4 types: power split, parallel, series, and series parallel. To avoid overcomplicating the topic, this video will focus on self-charging hybrids and exclude plug-in hybrids. While most automakers opt for the other 3 configurations, only Nissan and Japanese compact car specialist Daihatsu have adopted the series hybrid system. Daihatsu uses this system in a compact SUV equipped with a 1.2-liter engine, and as I'll explain later, this actually makes perfect sense. Nissan, on the other hand, is the only manufacturer using it in larger segments, like mid-size SUVs and minivans. Which means, there's a clear reason why other car makers have chosen to steer clear of it. A parallel hybrid incorporates an electric motor and a clutch between the ICE, internal combustion engine, and the transmission, allowing the ICE to be disconnected from the drivetrain. The main advantages of this system are that we can leverage existing ICE platforms, and that the driving feel remains close to a conventional ICE-powered vehicle. However, the improvement in fuel economy is relatively modest. This architecture is adopted by automakers such as Stellantis, Audi, Toyota, and Hyundai. Furthermore, high-performance sports cars from the likes of Porsche and Ferrari utilize this system as well. A series hybrid uses the ICE exclusively to drive a generator, while the vehicle itself is propelled solely by an electric motor. It consists of the ICE, a generator, an inverter, a high-voltage battery, and a traction motor. Because the ICE is dedicated entirely to power generation, it is not involved in propelling the vehicle whatsoever. A series parallel hybrid builds upon a series hybrid by adding a lockup clutch, allowing the ICE to directly propel the vehicle depending on driving conditions. At low to medium speeds, where electric motors are highly efficient, the clutch is disengaged, and the system operates as a series hybrid. During highway cruising, the ICE becomes more efficient, the clutch engages, and the ICE takes over to propel the vehicle directly. Some models also incorporate a 2 to 4-speed transmission, in addition to the clutch to further optimize efficiency. This architecture is adopted by automakers such as Honda, Mitsubishi, and several Chinese manufacturers. Combined with its excellent fuel economy and an acceleration feel close to that of a pure EV, it might be considered one of the most well-balanced systems. The power split hybrid architecture is predominantly used by Toyota, Ford, and Subaru. This system consists of an ICE, a planetary gear-type power split device, MG1, motor generator, which mainly operates as a generator and starter motor for the ICE, and MG2, which is primarily used to propel the vehicle. From a standstill to low-speed driving, the vehicle operates in EV mode, with MG2 solely propelling the vehicle. Once the vehicle speed exceeds a certain threshold, the ICE is started to provide propulsion. At this stage, the power split device functions as a CVT, continuously variable transmission, allowing the ICE to operate within its most efficient speed range. Compared to other systems, it is widely recognized that this architecture offers some of the highest fuel efficiency. This channel prepared a video that explains power split and series parallel hybrid in detail. If you're interested, please check it out. You'll find the link in the description. Let's consider the advantages and disadvantages of series hybrids compared with series parallel hybrids. Series parallel hybrids need an oil pump that generates hydraulic pressure to operate the lockup clutch, which causes energy loss. Series hybrids are also equipped with an oil pump, to lubricate and cool the motors and gears inside the unit, but it does not need to generate high hydraulic pressure. As a result, in the low to mid-speed ranges, losses are minimized, resulting in superior fuel economy. This helps explain why Daihatsu adopted a series hybrid system for its compact SUV, where high-speed fuel efficiency is not a major priority. In fact, the first vehicle in which Nissan adopted this system was a compact hatchback with a 1.2-liter engine. The drawback is high-speed fuel efficiency. There are two reasons for this. The first is the characteristics of electric motors. These graphs show the typical torque curves of a gasoline engine and an electric motor. You can see that gasoline engines are most efficient in the mid-speed range, while electric motors are highly efficient at low speeds. For this reason, series parallel hybrids engage a lockup clutch and switch to engine drive mode during highway cruising. However, series hybrids must continue using the electric motor even when its efficiency is low. The second reason is the repetition of energy conversions. In a series hybrid, the engine's mechanical energy is first converted into electrical energy by a generator. Since the conversion efficiency is not 100%, some energy is lost during this process. The generated electricity is alternating current, with a frequency based on the engine speed. This is converted into direct current by the traction inverter, where energy is also lost. To obtain the traction motor speed requested by the driver, the inverter converts the direct current back into alternating current, causing another energy loss. Finally, since the efficiency of the traction motor is also not 100%, energy is lost during motor operation as well. Consider a situation where the vehicle is traveling at a constant speed on the highway. Let us assume both engines have a thermal efficiency of 40%. In this case, since the series parallel hybrid is operating in engine drive mode, if we ignore gear losses, it can transmit that full 40% of the gasoline's energy straight to the wheels. In contrast, a series hybrid suffers losses at four distinct points: the generator, the inverter's AC to DC conversion, the DC to AC conversion, and the traction motor. Assuming each point operates at 95% efficiency, only 81% of the energy produced by the engine actually reaches the wheels. In other words, only about 33% of the energy contained in the gasoline is being used effectively. Nissan has introduced a series hybrid version of its mid-size SUV equipped with a 1.5-liter turbo engine, known as the X-Trail or Rogue, depending on the market, in several regions. However, it is widely rumored that the company abandoned plans to export this model to North America, its largest market, due to its poor highway fuel efficiency. Nissan brands its series hybrid system as epower. The epower system used in the Nissan X-Trail, or Rogue, is the second-generation version. The engine is a 1.5-liter 3-cylinder VC turbo. VC stands for variable compression. It is a groundbreaking engine that can vary its compression ratio between 8.0 to 1 and 14.0 to 1, using a complex multi-link mechanism integrated into the crankshaft. However, this expensive and complex system, while highly effective in a conventional gasoline vehicle, is arguably excessive for an engine dedicated solely to driving a generator. Let's compare its fuel economy with that of the power-split Toyota RAV4 and the series parallel Honda CR-V. All data is sourced from Germany's ADAC, Auto-Datenbank. First, let's look at the maximum power and torque of the ICE and traction motor. Compared to Toyota, which propels the vehicle using a combination of ICE and traction motor power, Honda and Nissan rely solely on their motors for propulsion, necessitating much more powerful electric motors. WLTP fuel economy. Since the unit is liters per 100 kilometers, a lower bar indicates better fuel economy. Toyota overwhelmingly outperforms the others. However, the fact that Honda's high-speed fuel economy appears worse than Nissan's seems to contradict the thesis of this video. But fear not. This is where things get truly interesting. To find the answer, we look to the real-world highway fuel economy tests conducted by the YouTube channel 1001 Cars. As these are real-world public road tests, environmental conditions vary slightly, and the drivetrain configurations, whether FWD or AWD, are not specified. Furthermore, because the current generation RAV4 has not yet been featured on their channel, we are utilizing data from the previous generation. While these figures may lack laboratory precision, they are more than adequate to capture the overall trend. Take a look at the results. As you can see, the core argument of this video is perfectly vindicated by these real-world numbers. Remember, standard WLTP testing consists entirely of transient driving cycles with continuous acceleration and deceleration, completely excluding steady-state cruising. Yet, when driving long distances, most drivers spend extended periods maintaining a constant speed on the highway. However, Nissan wasn't just turning a blind eye to this inherent drawback. In 2024, they introduced the Qashqai, equipped with their third-generation epower to the European market. While there were likely countless improvements, we're going to single out three major ones. The ICE was changed from the variable compression turbocharged KR15 DDT to the fixed compression turbocharged ZR15 DDTE. While adopting a larger turbocharger compromises low-end response, it significantly boosts efficiency within a specific engine speed range. This is an approach that would be impractical in a conventional ICE-powered vehicle. But it is possible with an ICE dedicated solely to driving a generator. In extreme terms, even if the ICE revs up 3 seconds after the driver presses the accelerator pedal, it would not be a problem, because the traction motor would accelerate the vehicle during that period. Based on this architectural approach, Nissan sacrificed some of the characteristics normally expected of a conventional ICE in order to achieve higher efficiency. The KR15 DDT has a peak thermal efficiency of approximately 38.7%, while the ZR15 DDTE achieves around 42%. Inside the inverter, the power transistors repeatedly switch the current on and off in order to convert direct current into alternating current. In the third-generation e-power, conventional silicon power transistors made way for highly efficient silicon carbide components. While silicon carbide transistors are becoming standard in battery EVs, where squeezing out every watt of efficiency is a top priority, their application in a hybrid vehicle is highly unusual. And the reason comes down to cost. In engineering, not just in the automotive world, cost and performance are always weighed against each other. Yet here, Nissan chose performance. Furthermore, Nissan improved the efficiency of the traction motor at high rotational speeds. They significantly reduced internal magnetic resistance, known as iron loss, which typically plagues motors at higher rotational speeds. Here is a conceptual graph to visualize this transition. Now, let's finally look at the data for the Qashqai, featuring the third-generation e-power, incorporated with all these improvements. First, we will compare the maximum power and torque of the ICE and the traction motor. Even without the variable compression mechanism, it delivers nearly the same power and torque as the previous generation. WLTP fuel economy. Unbelievable! Not only has it pulled far ahead of Nissan's previous system and Honda's, but it has even surpassed Toyota's. Now, here are the real-world fuel economy figures you've been waiting for. Astonishing! It is almost on par with Toyota's. Of course, this result comes with a few caveats. The Toyota used for comparison is an older model, and the Qashqai is FWD, while the drivetrain layouts for the other three vehicles remain unspecified. Furthermore, the Qashqai has a slightly smaller body than the other three, giving it a clear weight advantage. Therefore, we must keep in mind that this is not an entirely apples-to-apples comparison. However, one thing we can say for certain is that the evolution of the third-generation epower is truly remarkable. This summer, Nissan will introduce a new minivan equipped with the third-generation epower to the Japanese market. And Toyota's formidable minivans are already waiting for it. Looking ahead, this technology will undoubtedly filter down to the xtrail, known as the Rogue in North America. And that is when we will see the true potential of Nissan's latest hybrid evolution. Thank you for watching. If you enjoyed this video, please consider subscribing to the channel. We'll see you in the next video.